I remind you that last week we talked about multi-layer perceptrons, right? About basically layered nonlinear structures that we call neural networks, and we've seen also the convolutional part. We'll see more in the tutorial about convolutional neural networks. We concentrated mostly on how to compute the gradients of the neural network, right? We saw the backpropagation propagation technique, and the motivation for computing the gradient was that we need the gradient in order to do any useful minimization of the loss function, right? So today I would like to zoom in on this part, how to do supervised training of neural networks. Any neural network doesn't necessarily need to be a convolutional neural network or any particular architecture, any particular structure of the layers or of the nonlinearities. We'll just have a more general look. Okay, so I will assume that I know how to compute gradients, like we saw last time, and we'll see actually how to do minimization. So I will show you some very brief and elementary notions in numerical optimization, and next week we'll also dedicate some time to stochastic methods, which is something that is used for large-scale optimization problems, like the one we often encounter in deep learning. Okay. So I remind that this is our setting. So ideally, we would like to minimize the expected loss, right? So we have some pointwise loss that I'm denoting as L. It's pointwise loss, and we would like to minimize it over every possible hypothesis, right? And basically, we of course would like to be able to minimize this expectation over the unknown joint distribution of the instances and the labels written here. Okay. Of course, this is wishful thinking. Nothing written here is practical. So instead, we are going to minimize an empirical expectation. We are going to evaluate. We are going to approximate. Sorry, before. We cannot optimize over this object here. We cannot optimize over any function. We are going to restrict our functions to some hypothesis class. Usually this is going to be a parametric class, right? We saw that neural networks are exactly embodiments of these kind of classes of functions. The weights of a neural network, the weights and the biases are exactly those parameters that we would like to tune. Still, we cannot do this task because we have this expectation over an unknown distribution, right? So the next best thing we can do, we would like to replace this expectation by an empirical mean. Okay? So this is just an average of the pointwise losses on the training set. And obviously, we are going to try finding this minimizer. But in practice, we are going to run an optimization algorithm that will give us something that maybe comes close to the minimizer, but not exactly, right? So we'll have some tolerance epsilon here that will give us an approximation to the minimizer. Okay? So basically, this is what we would like to do. This is what we actually do. And there is some gap between these two objects. So the object that we would like to be able to find, this is our ideal hypothesis. And this is the actual object that we find by means of numerical optimization.
And that's because it's hard to find a minimum even for this problem.
Even for this problem, even for the problem with involving an in-sample loss, we will see that these problems are non-convex optimization problems. So at least from the theoretical standpoint, it's a hopeless problem to find the global minimizer of this problem. So we'll get something else. We'll get something that resembles the minimizer, maybe not. So at least there is very little theoretical justification for what can be done for a non-convex problem. Okay. Okay, so let's decompose the different sources of errors that we incur by basically going from what we would like to solve to something that we can actually do. Okay, so this is our expected loss. This is what we would like to minimize. And we can define what we can call the expected excess error. We will sample a training sample from the unknown joint distribution. We are going to restrict our function to a class of hypotheses, and we are going to minimize the in-sample loss instead of this function L, and we are not going to get the exact minimizer. So basically, this is the object we are getting instead, right? And obviously, it has some gap between the ideal loss that we would like to obtain on this minimizer of the ideal loss. We're going to get something worse, okay? And this worse can be actually decomposed into 3 terms. So this basically excess error can be decomposed into 3 terms. So the first term, I will call it the approximation error. So this is the error we pay by not optimizing over all possible functions from the instance space to the label space, but because we restrict our object of interest into some class of hypotheses. This is the approximation error. We are thinking of a hypothesis as an approximation of some unknown target function, of some unknown ground truth hypothesis, and we are approximating it, projecting it onto this space of functions. And it costs us some error. We call it approximation error. The next term is the estimation error. This is exactly the error we pay by not minimizing something in the real expectation, but taking a finite sample mean instead. Okay, so this is basically the finite sample error we are getting, and the final error term is the optimization error. This is what the imperfection of our optimization algorithm costs us. Okay, so let's analyze these 3 terms one by one. So first of all, the trade-off between the approximation and the estimation error, I'm using different colors here just for you to clearly see the different terms. Hopefully this color scheme is useful. So the approximation error is this term. It is the error we incur by restricting the model to some hypothesis class H. On the other hand, this is the estimation error. We call it generalization gap as well in the first lecture when we talked about generalization. And this is the error we incur by minimizing the in-sample loss instead of the expected loss, instead of the out-of-sample loss that we would like to be able to minimize, but we cannot. Okay? Now, the approximation error obviously will become smaller if we increase the size of the hypothesis class. If we put more complicated models, so instead, for example, instead of using linear hypotheses, we invented neural networks, right? We wanted something richer and with more degrees of freedom and with more representation capacity. This is exactly to get H richer. As the result, we are going to decrease the approximation error. Okay, and we've seen by hand waving what is called the universal approximation results for neural networks, that actually neural networks with enough parameters are universal approximators. They can decrease this error to an arbitrary small number, provided that the network is big enough. Okay. On the other hand, the estimation error is going to increase if we make the hypothesis class richer given the same sample size. We call this phenomenon overfitting. Okay, I showed you visual examples of overfitting. If our hypothesis is extremely rich, we can actually produce anything that fits the data perfectly on the training set. And of course, this might be completely useless outside of this training set. So what we can do instead is to increase the sample size. When the sample size is bigger for the same hypothesis class, the estimation error is going to decrease. Okay, we've seen concentration bounds for related to this n. Okay, so this is the obvious trade-off that we have seen between the approximation error and the estimation error. Now, how do we control the complexity of a class of functions? We would like some handle here. You see basically that there is a trade-off between these 2 errors controlled by the richness or the capacity of this hypothesis class H. How do we control it? So of course we could say that we have a neural network. It's not rich enough. Let's build a bigger neural network. Let's build an even bigger neural network. Obviously, this is a valid approach, but it doesn't give us any continuous handle to controlling the richness of the class. right? We need to reinvent everything. We need to build a completely distinct set of parameters. I would like some knob that can continuously increase or decrease the complexity of H. Okay, and the idea is called structural risk or structural loss minimization. So basically, we would like to use the same family of functions, but equip it with some hyperparameter C. And we'll put some term here. I'm calling it RH. Let's call it some function that evaluates the complexity of H. So I can take hypothesis from a very rich class, and I'm going to give some richness score to these functions. And then I would like to threshold and retain only functions that are not too rich. And the bigger is these parameter C, the richer is the class. So basically, I'm filtering, I'm creating a nested hierarchy of spaces of, let's say, the same neural network with the same set of parameters by measuring something in the space of parameters. Okay? And then the typical performance is going to look like this. So on the horizontal axis, I have this hyperparameter C. So here I have very rich classes. Here I have very poor classes. And on the vertical axis, I have the loss. So the in-sample loss is going to behave somehow monotonically, provided that of course, I can minimize it. I can always bring it to the global minimizer. I will see that the in-sample loss will monotonically decrease as I increase the richness of the class. And obviously, if the class is very rich, I'm going to perfectly fit my training data. Okay. Now, the expected loss, again, this is a theoretical exercise, provided that I can evaluate it somehow, will also decrease as I increase the size of the complexity of my hypothesis class. At some point, it will reach a minimum, and then it will start increasing. And this phenomenon of increasing this gap is called overfitting. Okay, this is exactly where we overfit. And this side is typically called underfitting, because basically we are not achieving what we could achieve by a richer class, neither in terms of the in-sample loss nor in terms of the expected loss. Okay? So if we could run the training with different values of the parameter C, we would select the just amount of C that gives us the best value of the expected loss, or some approximation thereof. Okay. Now, instead of working with this kind of inequality constraint, let's rewrite it in a Lagrangian flavor. We can simply think of adding some regularization term to the loss. Okay, so it will look like this. This is our original in-sample loss. Okay, function of H, or the parameters of H, and we're adding some regularization term to it with strengths controlled by the parameter lambda. Okay, so here the smaller is lambda, the less regularization we are demanding. So we are actually capable of taking very wild classifiers, very wild hypotheses from our family of functions, and the behavior will be more or less like in the previous plot, but now the meaning of lambda and C is reversed. So the smaller is lambda, the less regularization we are adding, and here we overfit. So it's an under-regularized scenario, and it means that we overfit. Okay, so the class is too rich, and here we underfit. Okay, and again there will be some optimal setting of this parameter lambda that we would like to take for minimizing the expected loss. Okay, now how do we estimate the expected loss? It's impossible, obviously, because we don't have access to the joint distribution of the instances and the labels. So what is done in practice is that we split our finite sample of the instance label pairs xi, yi. We split it into two disjoint, two independent sets, which we call the training set and the validation set. Okay, so basically think of two sets drawn IAD, drawn completely independently from this latent joint distribution. So there is no statistical relation between these two sets. They are drawn independently. And then we are going to find our model by minimizing the training loss. So all the optimization is done on the training loss. And we are going to evaluate. So we are trying to minimize the training loss, but we are going to evaluate the value of the same loss on the validation set. So these are samples that did not participate in the optimization. And we're going to approximate this estimation error by the difference between the validation loss and the training loss. Okay, so this is a proxy to actually computing the expected loss here, the out of sample loss. Okay, a question?
So why was this the estimation loss and not the one before it, the approximation loss? Because you're not finding the H star. You're getting the approximated one, aren't you? The red one.
Well, so basically, again, I would like to estimate. I would like to have an approximation.
You get the tolerance one.
So again, I would like to get an approximation to this quantity, to the expected loss, right? I can only compute it if I had access to the joint distribution and if I could evaluate the expectation with respect to the distribution. I don't have it, so what I do instead, I do a fine sample approximation, but on a disjoint and statistically independent sample, which I call the validation set. Okay. So in practice, we are going always to run training on the training set. We are going to plot on the same plot the training loss and the validation loss, and we are going to make decisions whether, for example, to stop the optimization algorithm by looking at the validation loss. Okay, and this can be thought of as another way of doing regularization. It is usually referred to as implicit regularization. We actually, if you think of how the loss behaves as the function of the compute time, or the number of iterations, if you will. So basically, as we increase the number of iterations, as we allow more and more time for the optimization algorithm to run, we are expecting the in-sample loss to decrease to some value, to some minimal value that that particular class of hypothesis or that particular regularization allows us to achieve, right? But maybe at some point, when we are optimizing too much, we start overfitting, and this is a very typical phenomenon. So then, if we could evaluate the expected loss, we would see that the expected loss decreases together with the actual training loss, the in-sample loss, and then it starts increasing again. Okay, so of course we don't have access to the expected loss. We evaluate the validation loss. Okay, so we replace this by the validation loss, and we evaluate it as the function of time. And when we see it increasing, we terminate the optimization algorithm. Okay, so we stop here. And you can think of this as some additional, some alternative way of regularizing the training. And there are many interesting properties, for example, of stochastic optimization algorithm that give them implicit regularization properties, and they are not fully understood as of today. So it's actually a very interesting and active field of research, basically, how exactly the specific choice of an iteration in the optimization algorithm carries with it some implicit regularization properties. And basically, some regularization properties are well known for many iterative algorithms, like conjugate gradients, for example. You can think of it in terms of projection onto a hierarchy of increasingly complex subspaces of space of solutions, and again, this is an active field of research for practical stochastic optimization techniques. So let's see now the trade-off between the estimation and the optimization error. Yes, a question?
How do you define capital L subscript v?
I just compute my in-sample loss on the validation sample. So again, what I do in practice is the following. somebody gave me my data, and this is all the data I'm going to get. And we can think about two different scenarios that I will mention in a second. I split this data into disjoint sets, and again, different practices tell which is going to be the proportion for the one set and which proportion for the other. I call one the training set. I do all the optimization on that set. So the loss, the in-sample loss on the training set is the training loss that I'm minimizing using the optimization algorithm of my choice. Then I keep the other set to just evaluate the loss. I'm not doing any optimization step based on that evaluation. I'm just plotting it together with the in-sample loss. So both are in-sample losses, but they're evaluated on two disjoint and statistically independent samples. Okay, and that serves as a proxy to the expected loss that I cannot estimate. Of course, the size of the validation set can also give me some confidence bounds, basically how well that in-sample loss approximates the actual expected loss. Okay, but I'm not demanding generalization from that loss because I'm not doing any optimization on that loss. Yes.
Why do you need both of them to estimate the out-of-sample loss, meaning the subset of examples of instances that you are not training on is a representation to the, let's call it, the real world.
So I need the basically my main demand is that the two sets, the validation set and the training set, they must be statistically independent, and they must be drawn from the same distribution, obviously. So in practice, I'm just randomly subsampling one big sample that I receive as my data and split it into validation and training. I'm doing all the training on the training set. So my estimator, my hypothesis is obviously biased toward fitting the training data, right? But I'm estimating my out-of-sample performance, my generalization performance on data that are distinct from the training data and have never participated in the minimization on the training sample. Okay, so this is a finite sample approximation of the expected loss, of the out-of-sample loss. Your question?
The implicit regularization with early stopping. This isn't special to neural networks. You can do this with any.
Of course. So everything I mentioned until now, and actually everything I'm going to mention today, is not restricted to problems using neural networks as our hypothesis. I can use it with any model. And we'll see that actually some techniques are used for specific classes of optimization problems. So we're going to talk about general optimization algorithms because there is nothing special about neural networks, nothing special about deep learning problems, maybe except the size of the parameter space and also the complexity of evaluating the loss because of the amounts of training data that we typically have. Okay, and I would like to address exactly this point. So if we go to the trade-off between the estimation and optimization problem, again, the estimation error is our generalization gap. This is the error we incur by going to an in-sample approximation of the expected loss. On the other hand, the optimization error is the error we incur but not finding the exact minimizer of the in-sample loss. Okay. Now, when we use bigger samples, we can decrease the estimation error because our in-sample approximation becomes closer. We have convergence guarantees actually, becomes closer to the expected loss, the law of large numbers essentially. Now, the optimization error, with a big caveat that I'm going to address next, is going to be decreased by spending more time on doing the optimization. Well, obviously, if you have some iterative process and you terminate it before it converges because you ran out of some imaginably allowed compute time, you're going to get a worse result if you run it twice longer, right? Right? If you allow it to converge for more time, it will give you better result. And here we can distinguish between two different regimes. One regime would be the small scale regime, and in the small scale regime, compute time is not an issue. Okay, so imagine that you have a problem that is fast to evaluate. You have the loss function is fast to evaluate. The optimization algorithm is fast to run. You don't have memory problem. You don't have compute time problem. So compute time is not an issue. Okay, so then you are limited by the size of your training data. You are limited by n. Okay, so your n and the size of your hypothesis, the number of parameters, is so modest that you can run any algorithm of your choice, and the compute time you have will be sufficient to make it converge fully. In that case, this optimization error can be made insignificant if you are able to find global minimizers. Okay, and there is some magic for neural networks that you don't find a global minimizer of a non-convex problem, but you find one of the local minimizers that is good enough, that is not much worse than any other local minimizer or the global minimizer. Okay, so basically it looks like there are interesting theoretical justification for that for deep neural networks, the landscape, basically the optimization landscape of the loss function that we're minimizing is actually very bad. It has many local minima and many saddle points, but all the interesting extremal points that are not saddles actually have more or less the same value of the loss. So that's why local minima are useful here. And we have, on the other hand, the large-scale regime. In the large-scale regime, think of the large-scale regime a situation in which evaluating, even just computing the in-sample loss function is extremely or even prohibitively costly. So imagine you have 1 billion of samples. Just writing this sum over 1 billion of samples, it will simply kill your performance. You will need to bring zillions of data points from memory to your CPU, do the computation, then bring them back out of memory. So just this will kill your performance. So then you never compute the loss. Entirely. So you use stochastic optimization. You compute an approximation of the loss on a small set that is called mini batch. We'll see it next week. And then using this approximate optimization can actually decrease the estimation error in this large-scale regime because you are going to be exposed to bigger sample sizes. Okay, so you are doing some optimization tricks that allows you to crunch in a limited compute time. Here you are limited by the compute time to crunch as many samples as possible. And in this case, we want to crunch as many samples as possible in order to decrease the generalization gap, the estimation error. Okay, so that's why stochastic optimization is justified in the large-scale regime. Otherwise, it is not well justified. It has some regularization properties, nice regularization properties, but otherwise, working with full batches, basically in a non-stochastic way, works better. Okay. So basically, let's now talk about how to do the optimization. And again, our goal is to bring to minimum this loss function, this in-sample loss function. So I'm now rewriting it in terms of theta. Theta is my set of parameters, the weights and the bias terms that we've seen for neural networks last week. Okay, so I have a hypothesis h theta. So I'm just packing all these non-linear and highly non-trivial form of this family of functions into the loss function. Okay, to me it's just a function of theta, and I would like to minimize this function with respect to its parameters, to theta. Okay. So again, we have a function from Rn to R. I'm calling by n the total number of parameters in my model. And in neural networks, it can be really millions or tens of millions. And I would like to find the minimizer of this function. Okay. So here we can distinguish between what is called the global minimizer. So the global minimizer is a point that we typically call theta star. It's a point, the value of the function at which is non-superior to the value of the function at any other point. Okay. So you cannot do better. You can do maybe the same, but you can get the same value of the loss, but not better. This is called the global minimizer of the function. And then we can distinguish it from the global minimum, which is the value of the function at the minimizer. Okay, so it's the difference exactly between the min and the argmin. The minimizer is the argument of the function that gives the minimal value of the function, which is called the minimum. Okay, and will be sloppy and we'll call them minimum most of the time, both the minimizer and the minimum. Okay. And what we can distinguish this, we can distinguish this from the local notion of a minimizer. So a local minimizer is a global minimizer in a small vicinity of a point. Okay, so just think of your loss function as some landscape, some elevation of some terrain. This is a two-dimensional example, and you are in a valley. Can you actually know that you are at the lowest point on Earth? No, because you don't have visibility for what happens outside that valley. Okay, so within that valley, as long as you can see around yourself, you are in a minimum. But maybe there is a much lower valley and much lower minimum somewhere that you don't see. So this is exactly this example. This is a local minimum. With this limited horizon, you think of yourself as a global minimizer. Okay, so within that ball, within that small environment, you are a local minimizer, but actually the global minimizer is here. Okay. So basically, a local minimizer is a global minimizer on a small domain, on a small ball centered around the minimizer. Okay. Now, what is nice about local minimizers is that we can easily characterize them by local properties, by using derivatives, and this is something that can lead us to efficient optimization algorithms. So I'm sure you know all this, and I also put some write-up on this elementary differential calculus on the website. But let's just recap what we know about local characterization of different extremal points of local minimizers, essentially. So let's assume that our function is C1, which means that its first order derivative exists and it is continuous. And let's do the first order Taylor expansion of this function. Okay, so the Taylor expansion looks like this. It has two terms. So where I'm fixing some theta, and then I'm looking about small displacements around that point. This displacement is denoted by vector d. Obviously, d is a vector in Rn, right, as well as theta. So first order approximation means that I'm going to linearize my function. I'm going to approximate it by a linear function, by a hyperplane, okay, tangent to the graph of the function. So this approximation is exact up to errors of second order in the norm of d. And the first term, the constant term, is the value of the function at point theta. The second term is the slope, or if you will, the normal to the plane that approximates linearly my function. Okay? So basically, I'm going to find a linear or an affine function, to be precise, that has the same value and the same slope as my function at point theta. Okay? Now, if I have theta star, a local minimizer, let's take a small alpha, a small positive alpha, and make a step in the direction of the negative gradient with respect to theta star. So this is my d. Okay, this is my d minus alpha times the gradient at theta star. Okay. So obviously, this well, I can write here greater or equal than 0. Okay, so I don't know if theta is a local minimizer. If alpha is sufficiently small, I fall within that small environment where I cannot, where basically theta star is a global minimizer. So I cannot be better than the value of L at theta star. Okay, so that's why I'm lower bounding this difference by 0, and I'm dividing by alpha. Alpha is a positive constant. It doesn't change this inequality by anything, right? So now let's substitute here the actual theta. So this is my theta. It's theta star minus alpha times the gradient. And now let's substitute the Taylor approximation. Okay, so this is the Taylor approximation. So this thing will be gone with the constant. Will cancel the constant part of the approximation. So I'm only left with the negative linear part, right? That depends on the gradient, plus this second order residual that I have here. So let's now cancel the alphas. I can cancel this alpha with this alpha. Here the alpha will be squared, so one alpha here will survive in the second term. So I'm getting this. Okay. Now, what is written here, this inner product between the gradient and the gradient itself, is the norm of the gradient squared. So it's minus the norm squared, plus alpha times some constant times, again, the norm of the gradient squared. Okay, and I can take alpha down to 0. It can be very small, a very small, arbitrarily small positive constant. So this term becomes insignificant, and this term is negative. Okay? So if this term is negative, by taking alpha to be sufficiently small, I can make this part to be smaller or equal to 0, right? On one side. On the other side, I know that it has to be greater or equal than 0. Okay? So there is only one number, there is only one value that this norm can have that is simultaneously smaller or equal than 0 and greater or equal than 0, and this value is 0, right? And if the norm of a vector is 0, it means that the vector itself is also a 0 vector. Okay? And this gives us what is known as the necessary optimality condition of first order, which tells us that if theta star is local minimizer of L, then necessarily the gradient at theta star will vanish. Okay? No surprises, right? Because if the gradient doesn't vanish, we can make a very small step in the direction of the negative gradient and decrease the value of the function, contradicting the fact that this is a local minimizer. Okay? Makes sense? Now, this is a necessary optimality condition. So any optimum, any local optimum, any local minimum has to satisfy this condition. But it is insufficient. Okay? So in order to see what will be sufficient, we'll need to go back to Taylor expansion. Now I will assume that the function is C2, meaning that it has continuous second-order derivatives. And I will add a second-order term to the Taylor expansion. This is my second-order term. And basically, second-order quantity, it means that I'm approximating my function as a quadratic function that has the same value at theta, the same slope at theta, and also the same curvature at theta. Okay? So the second-order term is responsible for curvature. Now, the matrix that you can see here, this n by n matrix, is called the Hessian matrix, and it is simply, at least in the standard basis, it is represented by a symmetric n by n matrix with all the second-order derivatives of L with respect to theta. Okay? And the C2 condition guarantees that this matrix exists, and it is symmetric. Okay, so by symmetric, of course, I mean that H transpose equals H. Okay, and now I can take a direction D and evaluate the curvature in the direction D. In geometry, you can call it directional or sectional curvature, and it will be given simply by this quadratic form. Okay, D transpose HD. It is like defining a new function of a scalar argument by taking a section in the direction D through the function L and measuring its curvature. Like it will be approximated by a parabola, by a quadratic function, and we can ask how curved this parabola is at the point theta. Okay? Now, this definition of curvature allows us to distinguish between 3 different types of points where the gradient vanishes. Okay, so the first order optimality condition holds, the gradient is 0. So the gradient is 0, it means that the hyperplane that is tangent to the graph of this function is flat. Okay, if it were inclined, we could decrease the value of the function further. Now, in this case, look, we are standing in this point, theta star. The normal, I'm defining the normal to the graph of the function is this green vector pointing outwards, okay, pointing down, okay, and I'm making a small step in this direction here. Okay, what happens to the normal vector? It rotates, and it rotates in the direction of the step. So if I project the difference in the normal vector, its projection onto the direction of the step will be positive. Okay, and this is what we call positive curvature. So we'll say that the directional curvature will be positive or non-negative for every d. Okay, now let's describe this in algebraic forms. Our curvature was defined as a quadratic form with the Hessian matrix at point theta star. Okay, it means that the quadratic form is non-negative in every direction, it means that the matrix is a positive semi-definite matrix, right? This is how positive semi-definite matrices are defined. It means that the Hessian basically has no negative eigenvalues, right? This is just the same statement made in the eigenbasis of the Hessian. Another possibility is that we have, again, vanishing gradient here, but now in every direction that we're making a step, the normal rotates in the opposite direction to the step, okay? And in this case, we'll say that the curvature is negative for every direction d. It means that the matrix is actually negative semi-definite. It means that all the eigenvalues are negative, right? Or non-positive. And this point will be called the local maximum. Okay? Now, the third possibility is what is called a saddle point. Here, again, the gradient vanishes, but there will be some directions in which we have positive curvature and some other directions in which we have negative curvature. Like you see, this direction has positive curvature, this direction has negative curvature. And in this case, the Hessian matrix will have both positive and negative eigenvalues. This is called a saddle point. Okay, it's neither a minimum nor a maximum. Okay? And of course, in order for a point to be a local minimum, we need the curvature to be positive. Okay? So we need, and this will be a sufficient condition. We need the necessary condition that the gradient vanishes and a sufficient condition that the curvature is non-negative. This will be our condition for a local minimum. Okay? Now, there is a set of functions in which the second order condition, the condition of the curvature, is satisfied automatically. And these functions are called convex functions. So for convex functions, the first order condition is both necessary and sufficient. So it is sufficient for a convex function for the gradient to vanish in order for the minimizer to be, in order for the point to be a local minimizer. And in convex functions, local minimizers are also global minimizers. Okay. So in order to define convexity, let's first define what is a convex combination. I will take two vectors u and v in a vector space. Actually, the definition is very general, but let's restrict our attention to a particular vector space, which is Rn. So I have two vectors u and v, and I will take a linear combinations of these vectors with coefficients that are non-negative and sum to 1. Okay. Okay. So a linear combination with coefficients that sum to 1 is called an affine combination, and if I'm also adding the condition that the coefficients are non-negative, it is called a convex combination. Okay. So geometrically it describes a line segment connecting between the points u and v. Okay, so lambda describes where exactly we are located on the segment. If lambda equals 1, we are located at point u. If lambda equals 0, we are located at point v. And by varying lambda from 0 to 1, we are filling this line segment. Okay? And the convex set is a set in Rn that is closed under the convex combinations of its points. Okay, so any 2 points we are going to any pair of points we are going to pick up from the set, the convex combination of these points will also be lying in the set. Okay. So, for example, this is not a convex set because I have 2 points with a convex combination that has points outside the set. This is a non-convex set. Okay. Now, how does this relate to functions? Well, let's first define, I would like to define convexity of a function in terms of convexity of a set. For that, I will need the notion of an epigraph. Okay, so what is a graph of a function? A graph of a function is this line, right? It's the set of points of the form theta and lambda theta, right? It is a subset of Rn plus 1. Okay, and this is also a subset. And an epigraph will be the set of points theta and L such that L is a lower bound on the value. L is no lower than the value of the function at the point theta. So it means that I'm also adding what lies above the graph. That's why the name epigraph. It's above the graph of the function. It's a set of all the points in Rn plus 1 that lie above the graph of the function. Okay. And my definition of a convex function is a function such that its epigraph is a convex set. So if the epigraph, if and only if the epigraph is a convex set, if and only if the function is convex. This is my definition of convexity. And of course, I can, by invoking the definition of convexity of a set, I can simply say that if I have 2 points on the graph and I'm connecting them by a chord, and I'm taking some point on the chord, the value of the function will lie below. Okay? So this is the textbook definition of convexity of a function. Okay, but I think this geometric definition is nicer, it's more compact.
Any given 2 points, right?
Any given 2 points.
So that drawing is perfect here.
Well, of course, so in this case, for example, there will be these 2 points that violate this definition, right? So it's every 2 point and every lambda, any convex combination. Okay? Now, just a brief recap basically of the huge difference between convex functions and non-convex functions. So for convex functions, we have no negative curvature. And you can actually, I didn't prove it to you, but you can actually see it from the drawing, right? The convexity means that I cannot have dents inside the epigraph, right? So the epigraph has to be a convex set. It means that it will have non-negative curvature. If we have negative curvature, we necessarily violate convexity. And in non-convex functions, we might have negative curvatures. Okay. So by the way, what is the logical opposite of non-convex of a convex function? It's not a concave function. Okay. So the logical opposite of a convex function is a non-convex function. A concave function is a function such that minus that function is a convex function, right? So you just flip the axis of the graph, right? The one that measures the value of the function. You just mirror it upside down, and then you get a concave function that instead of having minima, it will have maxima, right? But in general, a general function that is not convex and is a non-convex function, not necessarily concave. Concavity is as good as convexity if you want to maximize the function. Now, in convexity, for convex functions, local minimizers are also global minimizers, and this is not true for general non-convex functions, because they might have plenty of local minima that are not necessarily or arbitrarily far from being a global minimizer. Okay. Now, because convex functions have no local minima that are also not global minima, we can use descent algorithms, something that resembles or is a smarter version than the gradient descent that we have seen last week. We can start from some arbitrary initial point and do steps that decrease the value of the function until we roll into the minimizer of the function, and that is going to be guaranteed a global minimizer of the function, right? But there might be more than one minimizer that gives the global minimum, but we are going to necessarily find one of them if we work hard enough, right? For non-convex functions, there is practically no way to find a local minima. So of course, with these techniques, we are going to find local minimizers, but there is no way in general to guarantee that this local minimizer is going to be useful and it is going to be close to the global minimizer, because in most cases, it will not be anything related to the global minimizer. Okay? And again, we are not completely, but we are somehow ignoring this fact that all our problems we are going to work with are non-convex. Still, optimization techniques work well with deep neural networks. Okay? And there are some partial theoretical justifications to that, but it's kind of a magic that happens. Okay? Okay, let's do the break and we'll start talking about optimization methods themselves. So I hope that I didn't tell you too much new information, right? This is some elementary stuff. But let's now try to use the fact that we can have a local characterization of local minimizers in order to build actual optimization algorithms. And this is something that I would like to spend our time on now. So I would like to introduce you with a very general family of algorithms that are called descent methods. So in descent, every descent method, every algorithm in this family works like this. We start with some initial point that I'm going to denote as θ1, and then we are going to iterate until convergence. Okay, and we already have in mind what is our stopping criterion, right? We don't really want the optimization algorithm to converge in machine learning settings, but we would like to stop it according to some validation loss, right? So we have some stopping criterion. Then we are going to do the following. We are going to choose the descent direction dk, okay? Then we are going to choose the step size eta k, and then we are going to update our current iterate that, remember, started with θ1. The next iterate, θ2 and θk plus 1, is going to be our current iterate plus a step of size eta k in the direction dk. Okay? And this is going to look like this. We start at some point and we zigzag through the landscape of our loss function until we stop, which is hopefully when we reach a local minimum. Okay, so this is a typical family of algorithms. This part is more of a magic, and it is problem dependent. If you know how to initialize your problem, then do it. Otherwise, you start with some random initialization, zero initialization. There are some basically practices, for example, that are good for deep learning that are used here. You'll see them in the tutorial. Now, until convergence, we already discussed how to stop. There are also different practices how exactly to stop. The main ingredient that distinguishes between the algorithms in this family is how to choose the descent direction. And we'll see different ways of selecting the descent direction. The step size is often overlooked. We'll see some ways of doing this on choosing the step size. For now, let's just assume that somebody tells us the step size. It can be, for example, a constant step size. Okay, and in machine learning context, it is often known as the learning rate. The step size in optimization is known as the learning rate. Okay, so I'll say a few words about the step size, but let's concentrate on the descent direction because this is going to be the major difference between the different algorithms. Okay. Now, let's do the following very intuitive and almost obvious thing. Let's select D, producing the biggest decrease in the value of the loss function. Sounds reasonable? Okay. Let's write it like this. I would like to select D such that this difference before the step and after the step is maximized or minimized, because I would like to decrease the value of the function. So this will be negative. Basically, I would like it to be as negative as possible, right? So the magnitude, of course, is maximized, but the actual value is minimized. Okay. Let's plug in a first-order approximation. This is the linear part of the Taylor series. Of course, this term cancels the constant part, the zeroth order part of Taylor's approximation, and we are left just with this inner product of the gradient at point theta with the direction d. Okay. Now, what is the direction that will minimize this linear term? Okay, so let me make one step back. First of all, this problem is unbounded, right? You give me a direction that makes this value negative, I will multiply it by 1 billion, it will be even more negative, right? So this problem is unbounded, so I need to put some constraint on the d itself, right? So let's rewrite it. Let's say that the norm of d is 1, okay? Or any number, doesn't matter, because we really care only about the direction and not the size. The size will be taken care of by the step size, okay? So norm 1, and you may ask the next question, which norm? Okay, there are many ways to define a norm. Okay, and actually, if we select different norms, you will get different different choices of d, and all this falls under the definition of steepest descent. For example, if you select the L1 norm, you are going to select the coordinate in which the magnitude of the gradient is the biggest. Okay, it will lead to what is called the coordinate descent. But of course, the typical choice is the choice of the L2 norm. Okay, and the L2 norm leads to the negative gradient. Okay, so this algorithm variant of the steepest descent is called gradient descent. Okay, the direction of the negative gradient. Okay, so here's our friend. We are taking some step size in the direction of the negative gradient. Okay. Now let's take a quadratic function just for the illustration, and I'm not going to show you the actual derivation because it's simply lengthy algebra, but completely straightforward. Okay, so I will just show you a picture, and you can run it in Python or in MATLAB or whatever tool you prefer to use. You can run a few iterations and verify on the, let's say, a two-dimensional quadratic function that this is actually the situation. So I'm going to draw you. I'm going to, so I will put some. I will put some simple requirements. So first of all, I would like the Hessian to be lower bounded by some positive constant times the identity matrix. It means that no eigenvalue of the Hessian is smaller than m. Okay, and this is called strong convexity. Okay, so it means that not only I don't have negative curvatures, actually all curvatures are positive and bigger than a certain number that I call m. Okay, this is called strong convexity. Okay, and then I will also upper bound the eigenvalues of the Hessian by a big M. Okay, and this tells us that the gradient is Lipschitz continuous. So basically, that if I think of a gradient as a map, it doesn't blow up distances to unbounded. So if I take some set of points that I feed into this map that is a small distance apart, that distance will not be enlarged infinitely in the image of this map. Okay, so this is the definition of Lipschitz continuity. So it basically it behaves well. It doesn't change the scale too much. Okay, and this is exactly the scale is governed by the gradient of the gradient, which is the Hessian, right? And its maximum eigenvalue controls the scale. Okay, I will assume constant step size upper bounded by this constant twice the. So it's basically one over the average between the smallest and the biggest eigenvalue. Actually, other choices will work here as well. And then I can again derive. This is a simple derivation. You can do it yourselves. I simply don't have time to show it. Basically, you can see that the distance between the kth iterate of the gradient descent iteration and the actual minimizer, which in this case, in case of strong convex functions, is the unique global minimizer that the function has because of strong convexity. Actually, this distance will converge exponentially, basically down to 0, with a constant c times some constant that depends on how we initialize it, and basically this constant m of the Hessian, with basically some c bigger than 0. And for some reason in optimization theory, this exponential convergence is called linear convergence. Well, we can argue that maybe on a semi-log plot, exponential looks like linear, which is obviously true, but then anything on this plot will look linear. But anyway, this in the literature it is known as linear convergence. So it means that these numbers converge as a geometric series with the basis c. Okay, and c is called the convergence rate, the linear convergence rate. By the way, if we don't satisfy these strong convexity and Lipschitz continuity conditions, actually the algorithm converges sublinearly. So it's not such an optimistic picture. So it's not such a great algorithm. But what I would like to emphasize, I would like to actually examine with you is what happens to this c. So obviously there is some constant c that has a huge impact on how fast the algorithm will converge. So essentially it means that if I would like to decrease my what is called optimality gap, my distance to the minimum value of the function, if I would like to get it below epsilon, I actually need the order of log 1 over epsilon iterations to get there, right? I'm just taking the log of this relation here. Okay, so it is still quite important, but the constant here depends on c. So the constant, it might be a log of 1 over epsilon with a very big constant or a very small constant. So of course the practicality of gradient descent will depend on that constant c. So let's see two pictures. Okay. Yes, a question?
To ensure the Lipschitz gradient or the Lipschitz
Lipschitz continuity of the gradient. So you want to ensure Lipschitz property?
property. Can we use on a neural network which is obviously not convex any contraction operator before we update the weights and then ensure it?
So if you build your network as a sequence of linear operators with bounded eigenvalues and contractions that are Lipschitz, then you can guarantee that the entire composition is going to be Lipschitz.
Linear, but applying the contraction.
Well, a nonlinearity can still be a contraction, even if it is a nonlinear function. So actually, guaranteeing Lipschitz continuity of the gradient is not so difficult. Okay, even if the function is not C1, even if it is not C2, even if it doesn't have a Hessian, it still can have a Lipschitz continuous gradient. So Lipschitz continuity in this case, upper bound on the maximum eigenvalue of the Hessian actually implies Lipschitz continuity, but Lipschitz continuity doesn't need the function to be twice differentiable. Okay, but I would like to examine this basically in this setting C2 functions that have a Hessian matrix. Okay. So again, I'm drawing you two pictures. So this picture, think of a quadratic function, if you will. So these are the level lines of a two-dimensional quadratic function, and this is how the gradient descent algorithm converges here, more or less, right? It's my graphic. I drew it by hand. In this case, the small m and the big M is approximately the same. The eigenvalues of the smallest and the biggest eigenvalue of the Hessian is approximately the same. How can you see it from the picture? Well, you basically have two. So it looks like an almost isotropic ellipsoid or ellipse, two-dimensional ellipse, with two principal axes that are more or less of the same length, right? And the axes are controlled by the eigenvalues of the Hessian. And this is another example. In this case, obviously, the biggest eigenvalue is significantly bigger than the smallest eigenvalue, and you have a very elongated ellipsoid. And you see how many more iterations you need for the gradient descent to zigzag between the points until you reach the minimum. Okay. So another way of thinking of the eigenvalues in order to be scale invariant, obviously, if we are selecting the step size in some scale invariant way that depends on some average between small m and big M, is to define what is called the condition number, which is the ratio between the maximum eigenvalue and the smallest eigenvalue of a matrix, in this case the Hessian. And here the condition number is approximately 1. Here it's much bigger than 1. And we'll say that the problem is not well conditioned. Okay. Now, I am not going to prove this to you, but again, this is an elementary derivation that you can do yourselves. Just derive the distance between two iterates, and you will see that you can actually upper bound, at least asymptotically for general functions and exactly for quadratic functions, that the convergence rate will be adversely affected by the condition number of the Hessian. If the condition number is exactly 1, how many iterations do you need to converge? Just 1, right? The gradient points directly into the minimum. Just make a step of sufficient length and you are there. If you have a very bad condition number, you might need millions of iterations to decrease the value of the function, let's say 10-fold. Okay, everything depends on this constant c, which in turn depends on the condition number, right? Like condition number 1000, which is, we don't even call this an ill-conditioned problem. You will need thousands of iterations in order to decrease the value of the function 10-fold. Okay. Now, how can we improve this? How can we improve the behavior of the gradient descent? So let's do the following trick. Let's do a coordinate transformation. I have my original coordinates that I'm denoting by theta in red, and I'm going to apply some regular matrix P. P is an n by n matrix, which is regular. Okay, means it's non-singular. And I will define a new function. So I will call these new coordinates theta bar. denoted in blue, I will define a new function L bar, just not to abuse the notation too much. So L bar of theta bar is L of P theta bar. Okay, so it's just the same function rewritten in a new coordinate system. I will just use the chain rule to derive the gradient. Of course, here the gradient is with respect to theta bar. Here the gradient is with respect to theta. So it's just P transpose times the gradient of the original function with respect to theta, evaluated at point P theta bar, which is nothing than point theta. Okay. And for the Hessian, I do it the same. I do the chain rule twice. So basically, the matrix P will pop on both sides of the expression with the transpose on the left side and without the transpose on the right side. Okay. And if you don't remember these expressions, just go to the matrix cookbook, which is a nice reference on how to do calculus with matrices and matrix valued functions. Okay. And basically, what we have is this update of the gradient descent that I would like to write in both coordinate systems. Okay. So in the original coordinate system, we have this. This is our update. We are just doing regular gradient descent. Now I'm transforming to my new coordinate system theta bar, has to be bar. And this is my new trajectory. And this trajectory looks exactly like gradient descent. I have a different step size and I have a different gradient, right? This is the gradient of my L bar, okay, which I write like this using the gradient of the original function. So this is the gradient with respect to theta, to the red theta. Okay? And let's now do this trick. So this created a trajectory. Let's map it back to theta. Okay? So I'm just going to multiply everything by p on the left. Okay? I'm multiplying everything by p on the left. And this is the trajectory I'm going to have in the original space. Okay? You see it's a different trajectory. So basically I have this. I have one trajectory in the original space which converges according to the condition number of this Hessian matrix, and the green trajectory, it converges according to the condition number of this matrix, which is P transpose times the original Hessian. Okay. So then I can think of this as some way of improving the condition number. So if I choose my matrix P wisely, the coordinate transformation wisely, I can improve the condition number. And here you see the condition number improved because the green trajectory converges in less iterations. Okay? So what would be the ideal preconditioning? The ideal preconditioning would bring my condition number to 1. Then I converge in one iteration, right? What would be the matrix P that does this trick? It will be such a matrix so that P transpose H equals the identity matrix, or anything times the identity matrix for that purpose. So I will select P to be the negative square root of H. Okay, if I assume that my function is strongly convex, as I assume, of course this root exists, right? And the inverse exists. So with this choice, my iteration will look like basically, so remember P is H minus half, and I have P transpose appearing in the P transpose times H appearing in the preconditioned gradient descent step. So P transpose will be the Hessian inverse, right? Remember the Hessian is a symmetric matrix. Okay, so I have this Hessian inverse appearing basically as a scaling of the gradient, the stretching of the gradient. Okay. Now the problem is that we need the Hessian at the solution point, right, for this to work, but we don't know what is the solution point. Okay. So the next best thing we can do, we can evaluate the Hessian at the current iterate. So instead of writing it at theta star, we'll write it at theta k. Okay, and this is called the Newton iteration. Okay, there are many reasons why it's called the Newton iteration. You can think of it. So gradient descent was based on linearizing our function and then moving in the direction of the steepest decrease. Instead of doing a linear approximation of the function, I can do a quadratic approximation of the function. Then for a quadratic function, I have a closed form expression for the minimizer. And this I can go into that minimizer, and basically this will exactly coincide with Newton's iteration. So basically, it's a sequence of quadratic approximations of function. I'm moving to a new point, then I do a quadratic approximation again, and basically this is how I converge to a minimum. I can, instead of thinking of minimizing a function, I can think of finding the root of a gradient, of its gradient. Gradient equals 0. Okay, and how do I find the solution of some nonlinear equation? I can do a sequential linearization of that equation. I will linearize the gradient, find the root of a linear function, which is easy, right? It's solving a linear system of equations. Then I will stand at a new point. I will again linearize the gradient at that point, and again find the root of the linear system. This is exactly what happens in the Newton iteration. So both basically explanations give me the same expression. This is Newton's iteration. Okay. Now, by the way, can we precondition Newton's iteration to actually converge faster? Let's repeat the same trick. Let's do a coordinate transformation and find another coordinate transformation P that will make it converge faster. What do you think? Can it work? So it appears if you run the expressions, it will be very easy to validate. Actually, it appears that this iteration is invariant to any affine transformation of the coordinates. So it's some kind of canonical iteration. This scaling makes it invariant to any further linear preconditioning. Okay, if you have a nonlinear transformation, that's a completely different story. And there are methods like, for example, the natural gradient that has very interesting geometric interpretations that is actually invariant to practically any diffeomorphism that you use for coordinate transformation. Okay. Now, another very cool property of the Newton's method is that under not very strong assumptions about our function and the step size, it will converge quadratically close to the minimum. And by quadratic convergence, I mean this. So basically, this is the distance between the k plus first iterate and the value of the minimum. This is the distance between the kth iterate and the minimum. In linear convergence, we had this expression without the square, and we called it linear convergence. And in quadratic convergence, we have this square here. So on a semi-log plot, when Newton iteration goes close to the minimum, then suddenly the value of the optimality gap of this distance will drop quadratically to 0. Okay, so it converges very fast. So essentially, in order to do Newton's iteration, we can think of it as a descent algorithm, descent method, with a distance that we obtain from solving this system of equations, right? So basically writing. So I'm denoting by G this gradient at iteration k. Okay, this is H inverse at iteration k. So I can think of this H inverse k gk minus as dk. Okay, so it's just, so for in gradient descent we used dk equals minus gk, and here it will be minus gk scaled by the inverse Hessian. Okay, and scaling by the inverse Hessian is like solving the system of equations. The Hessian times d equals minus g. Okay, this is called the Newton system that we need to solve. Okay, now what happens in terms of computational complexity? So first of all, we need to compute the Hessian matrix. It is an n by n matrix. Okay, and unless we have some special structure, for example, some special structure will make this matrix sparse or somehow nicely structured. This is, by the way, what will happen, for example, if we have convolutional neural networks, because there are many dependencies between the parameters. So the Hessian will be a full n by n matrix. We need to store it. It's order of n squared. Computing it depends, of course, on the model that we use and on the loss. It can be computed by backpropagation the same way we compute the gradients, but still, computation will be of the order of the computation of the gradient times n, and the solution of the Newton system is the painful part. It's O n cube. Okay, solving a general system of linear equations is order of n cube. Okay, n cube means more or less that you can practically work with a few few thousands of variables, no more, right? Because otherwise the cube starts being very, very demanding. And in neural networks we have many hundreds of thousands or millions of parameters. So definitely this doesn't go to the large scale we care about in neural networks. Okay, scale in the sense of the size of the parameter space. Okay, how can we alleviate this computational burden? So let's concentrate on the solution of the Newton system first, and then see what we can do with the rest. Okay, so essentially one of a very cool family of methods that is called inexact or truncated Newton methods, or it's sometimes known as Hessian-free methods. I think Hessian-free is very confusing, but I will tell you exactly what is meant by Hessian-free. I would like to solve this system, hd equals minus g, I'm dropping the iteration indices, by an iterative method. So inverting a big matrix is no. Okay, so let's instead solve this minimization problem. Okay, I would like to find d that minimizes this expression. This is the discrepancy between left-hand side and the right-hand side of the equation, right? So if I find d that minimizes this discrepancy to some prescribed tolerance, then I'm good, right? So I found an approximate Newton direction. Okay. Now, if I write this objective function that I would like to minimize, I write its gradient, and you see in the gradient we have h product with d and h transpose product with d, right? So we don't really need to materialize all this n by n matrix H. We just need to be able to multiply by it and by its transpose a vector D. Okay? So if we are running, for example, gradient descent iteration here, we actually don't ever need to store the matrix H. We just need to compute it and be able to multiply by it. So again, this is done by methods similar to backpropagation. Okay? So in backpropagation, I don't compute the Jacobians of my neural network. I compute the Jacobian times some vector, right, which is the gradient of the loss. This is what we did in backpropagation. The same can be done with the Hessian. Okay, I can use backpropagation-like techniques to compute the product of the Hessian by some vector d. Okay, and it is in this sense that these methods are called Hessian-free. So you need the product of the Hessian with the vector, but not the Hessian itself. Okay, and typically this minimization problem is solved by a method which is called precondition conjugate gradients algorithm, which looks like gradient descent by in some transformed coordinate system. Okay, and again, this is a very beautiful algorithm. I have no time to describe how it works, but there are existing solvers. They do it very efficiently. It has the same complexity of gradient descent, much faster convergence. And it also uses exact line search, which refers to how we select the step size. Here the function is quadratic, so we can actually have an exact closed form expression of what would be the optimal step size. Okay, and this is called exact line search. Okay, so this is inexact Newton. Let's look at another technique or family of techniques, which is called Gauss-Newton approximation. The main problem of this inexact Newton is that we need if not the Hessian itself, we need the product of the Hessian with a vector. It might be computationally demanding to evaluate this product, or we might have a model that doesn't have a Hessian. For example, if you are using ReLU in your neural networks, it is not differentiable, right? So we don't want the Hessian to appear explicitly. Okay, so let's have a slightly closer look at our loss function that we're using. So remember, our in-sample loss function looks like this, right? It's a sum of the pointwise losses, which I will write again. I'm abusing the notation here a little bit, but basically it's sum of loss functions that I'm calling Li, which depend on the specific label yi. So I'm absorbing all these labels and the exact form of this pointwise loss function into a collection of functions that I call Li with the index I. And this function receives a vector, which I call y hat. which is the estimated label or the estimated label probability, as we have seen in multi-class classification problems, and it gives us a number. Okay, so basically I have two components to this loss. I have the pointwise loss function, which is typically convex. The cross entropy is convex. The quadratic loss is convex, right? And then I have the model itself. Okay, this is the output of the model. This is our hypothesis with the parameters theta. That part depends on theta, right? And this is typically non-convex. This is our neural network, essentially. Okay, this is the output of the neural network, function of its parameters. So basically, it's the neural network applied to the instance xi, and this is what I'm calling by y hat I. Okay, so I'm thinking of a function of theta. Again, yi is a map from Rn to Rk. Okay, n is the number of parameters, k is the number of output dimensions of my neural network, for example, k classes, into which I would like to classify the instance. And L, of course, is a function that takes that k-dimensional input that gives me a number. Okay. Now, let's take the model, which is a map between Rn and Rk, and write a first-order Taylor expansion. Okay, so it will look like a constant term plus the Jacobian times the direction d. Okay, so I'm doing a small displacement d. Of course, there will be some second-order term which I'm dropping. That's why it's an approximation. Okay, so let me write it compactly as yi hat, which as I'm just dropping that it is evaluated at theta, which is obvious, plus ji, which is the Jacobian at theta times d. Okay, and this Jacobian is obviously a k by n matrix. It's the gradient of a vector-valued function. Okay, so it's every row of this Jacobian is the gradient of each of the coordinates of the vector-valued function. Okay, output coordinates. Okay, so let's now get back to our loss, and I'm going to do the following. I'm going to substitute the linear approximation or the affine approximation of the model here, this blue part, and I'm going to do a quadratic, a second-order approximation of the pointwise loss of the red part. Okay, so I'm calling my displacement of the model. So let's do the quadratic approximation of the pointwise loss. My change of the model output will be denoted by delta. Okay, so this is the second-order approximation, and basically what we care about is this expression, right? Because it is governed by the Hessian. Okay, so this expression, now I'm substituting the exact form of yi hat. Okay, I'm going to substitute what is written here. Okay, so basically my delta will be exactly JID. Okay, so if I change my model parameters by d, the output of the model will change by JID. At least this is the linear approximation. And basically what you see here is the change of the loss under my quadratic approximation. Okay, so this is the quadratic part of my approximation. Okay, so it means that I can write it like this, and what is written here is my approximation of the Hessian matrix of the entire in-sample loss. Okay, of course I need to sum it over I. Okay, so basically this is my approximation of the Hessian. Now pay attention that we are using the second-order derivatives of the loss, which is a convex function. It has nice, simple second-order derivatives. And we are using only the first-order derivatives of the model. Okay? Now, basically, this technique was first proposed for least squares problems, when we have nonlinear least squares. So the loss itself is a quadratic function. Its Hessian is just the identity matrix, right? And the model itself is used only with first-order information, with first-order derivatives of the model. Okay. Now this Hessian of the loss will typically be positive semi-definite. Basically, this will be positive semi-definite or even positive definite. And if we use regularization, like I told you, for example, something like an L2 norm of the weights, which is called weight regularization or weight decay, it will actually be strictly convex. It will be positive definite. And if this loss function is positive, this expression will also be positive semi-definite. Okay? So basically my approximation of the Hessian will be typically positive semi-definite, which is nice, right? I must have my approximate Hessian positive semi-definite in order to guarantee that my direction is actually a descent direction. Okay? So for example, if we have the cross-entropy loss, like what we've seen in the case of classifiers, I can write it like this, and then the Hessian will be this simple diagonal matrix. So this 1 over y hat squared basically comes from the minus log derivative twice, right? So the second order derivative of minus log is 1 over the argument squared, right? And then we have these constants that come from the training set. Okay, these are the hot encodings of my ground truth class labels. Okay, and actually, the same way we do backpropagation, similar techniques can be used to evaluate basically these products of the Jacobians with these matrices. Basically, it generally falls into the category of automatic differentiation algorithms. It is exactly like backpropagation with an additional step that we need to do, and it is efficient. We never actually need to construct and store the Jacobian. We just compute the products of the Jacobian with something. Okay, so this is the Gauss-Newton approximation. Now, if this approximation of the Hessian has zero curvature, has zero eigenvalues, if we now invert this matrix, we will make infinite steps in those directions, right? So in those eigenspaces of the approximate Hessian that correspond to zero eigenvalues, in those directions our step size will be unbounded, right? So we need somehow to keep the step size small in those directions. And one of the ways of doing it in optimization is what is called trust region. We would like to add positive curvature to the model Hessian. And the bigger is this curvature, the closer we keep our steps to the original point. Okay? Basically, I have some force opposing to longer steps. Okay? And this can be done by adding a diagonal matrix to this model Hessian. One of the ways is to add some constant curvature to the diagonal, lambda times the identity matrix. Another possibility, lambda times the diagonal of the model Hessian. Yes? A question? Positive, yes, positive, of course. It has to be positive curvature. Okay? And so this is known as the Levenberg-Marquardt technique. There are some heuristics how to control the lambda in general in trust region methods. And this is actually the workhorse for nonlinear least squares and model fitting. So especially for small scale, if you have a modestly sized problem in terms of n, in terms of the number of parameters, this is one of the methods of choice. Works really well for nonlinear problems. Okay, so it's basically Gauss-Newton with this regularization of the Hessian. And you can think of it as adding regularization to the loss. For example, L2 regularization of the weights will exactly have the same effect.
H tilde here is the first order.
It's exactly this matrix here.
Yeah, it's the first order estimation of the model's Hessian.
It's the Gauss-Newton estimation of the loss Hessian, which is based on the first order derivatives of the model.
Hessian is the right H, not? According to your definitions, the loss Hessian is the right H.
Okay, so H tilde is basically this total formula for the loss Hessian. Okay, so the Hessian of the pointwise loss is Hi. So this is the pointwise loss, and this approximates the Hessian of L. Okay, for the entire loss. Okay, it's sometimes called the Gauss-Newton matrix. And again, we don't need the Hessian of the neural network itself here, just the Jacobians. Yes?
The approximation error or bounds on this or other methods?
Well, so you can try analyzing how well this Hessian approximates, in some sense, the original Hessian. I think it's not very useful. What is useful is what happens when you plug this as your descent direction into the Newton method. Okay, and actually it works very well. And there is theory. I don't think it is very relevant because the assumptions that you need to make in order to prove all these theorems are completely irrelevant. Okay, but in practice, it's one of the best practical choices you can think of. Okay, of course, it is limited by scale because of because the expressions become costly. So in neural networks, this is used for neural networks, especially for recurrent neural networks that have modestly sized parameter spaces. What is done there, basically, you try to push as much as possible to the loss function itself. So you repartition the distinction between the loss function and the neural network itself, the model itself. For example, softmax can go into the loss function, right? So you end up with negative log cross entropy loss, something like that. Okay, so let's have another look at Newton's iteration, and basically see. Still, even if we plug in our Gauss-Newton model Hessian here, we still need to solve the system of equations, right? We have the inexact ways of solving the system of equations. Still, we need to store the Hessian. Still, we need basically to do something with this inverse, either exactly or approximately. So another family of methods that is called quasi-Newton methods, they actually do a smart trick. We are going to model not the Hessian, but the inverse of the Hessian. Let's call it BK. So BK is going to be a model of the inverse Hessian, and we are just going to scale our gradient by, or negative gradient by this BK. So this will give us an approximate Newton direction, okay? And now another trick that is done is that we are not going to build this model of the Hessian at once. We are actually going to gradually update it as the iterations proceed. Okay, so we'll have some update scheme that will update this model of the Hessian, of the inverse Hessian BK. Okay, so let's do how we can model the inverse Hessian. So let's first see what conditions should be satisfied for the Hessian. I'm doing the first order Taylor expansion of the gradient. Okay, so the linear term in the first order expansion of the gradient is governed by the Hessian, obviously. P is my displacement. I'm fixing theta. Okay, so let's now fix theta to be theta k, and my displacement is going to be exactly the step between two consecutive iterations, k plus 1 and k. Okay, and this is what I'm going to get from the first order expansion. I will substitute gk, basically just as a shorthand for the gradient and theta k. Obviously, gk plus 1 is the gradient and theta k plus 1. And I'm going to get this. Let's reorder the equation. We have basically that the difference of two subsequent gradients is approximately equal to the Hessian times the difference between two consecutive steps. Okay? And this is called the second equation. I will just denote the difference of the gradients as qk. Two consecutive gradients, the difference is called qk. And this is called the second equation. Okay? And you can relate it to the second method for finding roots, for example, of polynomials or nonlinear functions in general. So I would like this second equation to be satisfied by bk for my last iteration, not necessarily for all the iterations that preceded it, but for my current iteration. So basically, I would like to design an update scheme for my inverse Hessian, or let's start with the Hessian itself, that satisfies, first of all, the second equation. Then I would like to maintain symmetry of the Hessian. Hessian has to be a symmetric matrix. And I would like to maintain positive definiteness, or positive semi-definiteness. Okay? So it appears that you can do a rank 2 update, actually do an additive update with a matrix of rank 2 to the model Hessian that satisfies all these three conditions. And this is called the BFGS update. Okay, and BFGS stands for the names of the people who invented it. Okay, so this is BFGS rank 2 update. Again, I'm not deriving you exactly the scheme, but the rationale is exactly satisfying those conditions. Now, wait a second. We don't need the Hessian. We need the inverse Hessian, right? So we have this nice rank 2 update. How do we get the inverse? And it appears that there is a very nice, again, use the matrix cookbook. It's really cool. basically there is this matrix identity that is known as the Sherman-Morrison, or in general the Woodbury identity. It tells me how to invert a matrix perturbed by some low rank matrix. So UV here will be rank 2. Okay, and in case of rank 2, so U is a very narrow matrix and V is a very thin matrix, very short matrix. So in this case, actually, I have H inverse, which is my inverse Hessian in the previous iteration, and this is a very simple term to evaluate because U and V are order of n times 2, right? And this is my update of the inverse Hessian that I'm going to get. Okay, this is actually the BFGS update formula for the inverse Hessian. Okay. Okay, so just to complete a few more things about BFGS, and then we'll next week we'll talk about stochastic optimization. So essentially, BFGS quasi-Newton method is a first-order method. We are never actually going to compute the Hessian. We don't even need any routines in our code that compute or do numerical approximation of second-order derivatives, right? We build a model according to the formula that I explained. And another important thing, we don't need matrix inversion. We don't need to solve any systems of equations. We actually model the inverse Hessian directly. Okay? It has superlinear convergence. It's actually quite impressive. So under very mild assumptions, it converges faster than linear. Again, superlinear, it means that remember this is linear convergence, right? With convergence rate C. Now, C will be something that depends on the iteration K. And if this sequence goes to 0 as the iterations proceed, it is called superlinear convergence. Okay, so basically the convergence rate goes to 0. It actually improves as we proceed. So it's really fast convergence. But we still need to store the big K, right? This approximation of the Hessian inverse will cost us n squared. So n squared means that you can work with maybe 100,000 variables, but no more, right? Because then the memory will kill you. Okay, so, but when you again look at this formula, if you want to do L consecutive updates, you really need to store these vectors P and Q from 1 to L, okay? And this takes order of Ln, or twice Ln, okay? Not n squared. And here we get to what is called the limited memory version of BFGS. Limited memory means that we would like to store, our memory allows us to store number of basically updates backwards, which is I'm denoting by capital L. It's a poor notation because L is our loss function, but this is how it is denoted in the literature. L much smaller than the model size, than the number of parameters. Okay, and there are many ways of doing it. There are some two-step recurrent formulas that, for example, exist in the literature. I'm not going into exact details, but basically you can construct this. What you need at every quasi-Newton iteration is the product of this bk with a negative gradient, and you can actually construct it on the fly from the stored last L, P, and Q vectors that you got from the steps and from the gradient differences of the previous L iterations. This is how limited BFGS works, and if Levenberg-Marquardt was the best choice for small-scale problems, this is the best choice for a large-scale problem. So if you have a general large-scale optimization problem, and you can afford evaluating the loss function, use LBFGS. Okay, this is really by far the best method you can imagine. This again brings us to medium scale in terms of the data size. If we have so many data samples that even evaluating the loss itself once is prohibitively expensive, both in terms of arithmetic and memory complexity, then the default choice, the best choice you can do, will be stochastic optimization, working in mini batches, and this is what we are going to see next week.
So I would like to proceed from the point where we stopped last time, and I would like to show you the last part that I was planning for this course, basically to show you stochastic optimization techniques. And you have seen already some of the most commonly used techniques like Adam in the tutorial. I'm insisting on showing you more just to make sure that you don't believe that there is only Adam that you run with default parameters and that's all. Basically, there is a wealth of different techniques. It is actually subject to active research in this field, basically to decide, to determine which exactly are the best techniques for deep learning. For example, there is a lot of interest in using second order or approximate second order techniques for deep learning, and many of them are actually employed, for example, for recurrent neural networks. So I would like to get back to the problem that we are trying to solve. We would like to bring this loss function, which we called initially the in-sample loss, right? This is just the empirical average of the pointwise losses on the training set. We would like to bring this to minimum. We are minimizing over theta, which is the collective representation of all the parameters, all the degrees of freedom in our network. Now let's see. First of all, the evaluation complexity of this loss function is the order of n, right? So if I assume that this individual loss takes me order of 1 to compute, then the entire function is the order of n. It costs me the size of my training set. And you have already experienced some applications, n might be very big, right? And we might call this regime the big data regime, right? Where our training set is huge, can be millions or billions of data points. So we have seen some claims about the convergence rate. I didn't have time, unfortunately, to prove you anything, but there are actually textbook results. So we have seen that, for example, first order methods in some favorable settings under some technical conditions converge what we called linear convergence, right? So we have this constant c to the power of k. K is the iteration number, right? So if we now do the opposite kind of reasoning, so I don't care about the convergence, I care about achieving some epsilon optimality. I would like to be epsilon far from my optimal value. Then I just take the log and I will get this number. So basically it will take me the order of log 1 over epsilon iterations to achieve epsilon optimality in this minimization problem. Okay? And the compute time I'm going to invest, and I'm completely ignoring all the memory problems that I might have, basically all these bottlenecks, and I'm completely ignoring the acceleration I can get by parallel computing. I can actually compute the terms of this loss in parallel. Okay, so I'm ignoring this. If I ignore this, then my entire amount of compute time that I'm going to invest is going to be of the order of n times log 1 over epsilon. Okay, and this is going to kill us for big N. So something linear in N. So remember my definition of big data. So big data is n so big that order of n is intractable. Okay, so if we are in this regime, then we cannot evaluate this loss function even not a single time. Okay. So I would like to propose an alternative, which is stochastic optimization. So remember what we did in the regular optimization, which in this context will be called batch optimization. Okay, batch means that we are evaluating the loss function on the entire training set in a batch. So what we had, for example, this is a gradient descent iteration, right? So, and of course we had different modifications of this iteration, and modifications came by putting some stretch, some scaling matrix here, be it the inverse Hessian or some approximation of the inverse Hessian or something else. But basically this is what we did, and it always gave us a deterministic trajectory, right? So of course it depended on the choice of the specific descent direction. It depended on the choice of the step size. But these are all deterministic decisions. We only need to specify the initial point. From the same initial point, we are going to always to have the same trajectory. Okay? And of course, the negative gradient is always a descent direction. And if we scale it by positive semi-definite matrix, it will still be a descent direction. Okay? The iteration cost, however, again, in these batch methods, is prohibitive for large n's because it is linear in n. And the alternative that we are going to consider is what is called stochastic optimization. So in stochastic optimization, I'm going to, at least this is the simplistic setting, I'm going to, instead of evaluating this gradient of L, of the entire loss function, I'm going to pick just one sample, let's call it IK. I will draw it randomly with uniform distribution from the set of all indices in my training set. I'm going to estimate my gradient on just that sample and make a step in that direction. Okay, sometimes it will be horribly bad, sometimes it will be good. Okay, so first of all, the trajectory is going to be a stochastic process. It's not deterministic anymore because we're randomizing at every iteration. The direction for every realization of this trajectory will be different. Okay, so first of all, the claim that we had that we had a descent method, it's not a descent method anymore because this direction is not guaranteed to be a descent direction anymore. Actually, sometimes it will increase the value of our function. But what will happen is that the expectation of this direction will be a descent direction. Okay, so it will be true under the expectation. Actually, this is an unbiased estimate of the gradient of the loss itself. Okay, so we don't have a descent algorithm anymore, but we have a stochastic optimization algorithm. We'll call it stochastic gradient. And I insist on naming it stochastic gradient and not stochastic gradient descent, as it is named in many papers and books, because this is not a descent method. And what is important is that the iteration cost now is order of 1. It doesn't depend on n. So theoretically, we can work here with unlimitedly big training sets. Okay, so let me spend some time in the next hour to analyze what we are going to get from this algorithm, or actually from this family of algorithms. Okay, so this is our simplest stochastic gradient algorithm. In statistics, this approach is called stochastic approximation. Okay, and we are simply taking the regular gradient descent algorithm and we are replacing the gradient with this, which is an unbiased estimate of the gradient of the loss. Okay, but we are evaluating it at a single point, which costs us nothing practically, just single gradient evaluation. Okay. So I will show you some results related to the convergence analysis of this algorithm, and then we will see a little bit more, slightly more delicate analysis when we talk about the choice of the step size. Right? Currently, we completely overlooked the choice of the step size, so we assume that somebody gave us this eta k at every iteration. So we'll get back to it. So in stochastic gradient descent, we can guarantee what is called sublinear convergence. So first of all, it is only guaranteed in expectation because we have a random process. But in the expectation, the distance of the kth iterate from the optimal value is of the order of 1 over k. Okay, so previously we had c to the power k. It was a geometric series, which is in optimization theory called linear convergence. This is slower than linear. Okay, so c to the power k converges much faster than 1 over k. Okay, so if in a semi-log plot, c to the power k looks like a line, this is what gives the name to linear convergence. This is sublinear convergence. It's worse than a line. It's slower than a line. Now, in order to get epsilon optimality, we need 1 over epsilon iterations, which is much worse than order of log 1 over epsilon iterations, clearly, right? But so this is what we had in the batch mod. At least in favorable settings, we had linear convergence, and epsilon optimality was achieved in order of log 1 over epsilon. So of course, convergence is slower if you count the number of iterations. But let's now count the computational complexity. Here, the computational time was linearly dependent on n. Here, the computation time doesn't depend on n at all. Okay, so when n is big, then this advantage of having log 1 over epsilon over just 1 over epsilon starts being negligible because of the big factor that appears here. And this is exactly where stochastic gradient descent or stochastic gradient algorithms start winning over the batch optimization algorithms, just to show you a typical plot. So what is plotted on the horizontal axis is the number of data points that I have accessed. Okay, so just think of the number of data points I have accessed as some units of computational complexity, right? Because every point I access, I compute the gradient. Let's say this is 1 unit of time. Okay, the more I compute, my time, the entire compute time scales linearly unless I'm doing some parallel processing. Okay, so this is the typical convergence of BFGS. And I don't know where the iteration numbers were, but more or less it will look like this. You can see the iteration numbers here, more or less, right? Something like this. So it converges fast. It converges damn fast in very few iterations, but every iteration takes a lot of time because it is order of n. And this is how the stochastic gradient converges. It has 2 very prominent features. First of all, it converges very fast in the beginning. Okay? Very fast, much faster than LBFGS, which is probably the fastest of large-scale batch methods. And then it takes a lot of time to improve, and then it stalls and doesn't make any progress. Okay? So this is a fixed step. This is a fixed step stochastic gradient that I'm showing here again. Pay attention to the remarkable drop in the loss function in the beginning, much faster than LBFGS. And this is very typical, okay? Because here we are making many iterations, but each iteration is very inexpensive. Yes, question?
This is the entire loss function evaluation. The entire loss function descent this fast.
Okay, so what is plotted here again is LBFGS runs on L, on the entire loss function, and let's ignore what we are we also need to build the model for the inverse Hessian. We are building it using this 2-step recursion that typically is used in LBFGS, but this time that takes us to get from one iteration to another is dominated by the number of points that we are summing over the loss function, or its gradient, actually. So we're evaluating the gradient at every point on the training set, and this costs a lot of time. So every iteration is very long. Here, I don't know what is the time elapsing between one iteration and another. It's a very short time, because every iteration costs you n times less than LBFGS. Another question? Yes. So the remark here was that there is no evidence of time, no indication of time in this plot, and this is incorrect. The evidence of time is the amount of data points that we have accessed. So I'm ignoring memory bottlenecks and parallel computation. On a purely sequential machine, the number of points you accessed is the time that you spend on doing optimization. It's the total, the cumulative time that you spent accessing the data points. Of course, multiplied by some amount of time it takes you to compute the gradient of Li, and this is your computational complexity. This is exactly time. I could write it in seconds. It would be just a linear scale up to some platform-dependent variability. But it is very accurate for such scales. Okay, question? It's just one sample. The batch size here is one sample. Okay, so I haven't talked about mini batch mode that you are probably referring to yet. Okay.
You took a number of points and calculated the gradient on them, right?
I took 1 point and I calculated the gradient on it. Okay. Yes.
How do you the empirical risk? Don't you need to compute on all the samples the loss function?
So if I work in batch mode, I need to compute the gradient and the loss function on the entire training set. What I'm doing instead, I'm taking a very bad, unbiased estimate of the gradient at the current point by taking just one sample.
So how can you compare them? So how do you know that the empirical risk of the entire data set is better than LBFG?
What is plotted on the vertical axis is L, which is evaluated on the entire data set. Okay, or actually this should be, at least this should be for practical purposes the loss on the validation set, but here it is the training loss. Of course, it took a lot of time to compute this part, but this is just for visualization purposes. Okay, actually the validation loss is not computed at every iteration. Okay. Okay, so the question was, why do we see monotonically decreasing behavior of stochastic gradient? Because this is an averaged plot. So actually it has many hundreds of thousands of points here, and they are averaged in a big time window. So you actually see the average. Otherwise, it would be quite significantly oscillating. Okay. Yes. So the question was, why do we insist on sampling the gradient at one point? Of course, there is actually an interesting trade-off. I will show it to you later. Okay. So let me just show again this typical behavior. We are very fast in the beginning, and then we stall and remain somewhere, some envelope around the optimal value. So let me show a very simple example adapted from Berseca's, adapted from Botu. Okay. So what we have is each individual Li is a quadratic function, just theta squared centered at some point, and it is centered at a point in the interval from -1 to 1. Okay, and the points in this interval are completely uniform. So think of them as our yi's or xi's. It doesn't matter. And of course, the expected loss is this red quadratic function, which has the same constant and slightly raised constant. Basically, it will be alpha. It will be theta squared plus, I think, 1/3 or something like that. So essentially, suppose I'm starting here. Okay, I'm starting outside this interval. So when I'm starting outside this interval, the first iteration will bring me very fast toward the interval, right? Because the cost here, the loss here is really huge. So the gradient is high. No matter whether I take this sample or this sample, the gradient is still very strong in the direction of the interval. Okay, this is just a one-dimensional example, of course. So I will be progressing very fast toward the interval, and then in the interval, I'm going to stall. Once I enter this interval, which is exactly that envelope that I tried to plot in the previous graph, I'm going to just jump back and forth according to the exact sample that I'm going to draw. Okay? And nothing will improve from this point on. So I need somehow, and pay attention to another thing, if I take a big step size, I'm going to reach this interval very fast. Much faster than if I take a small step size. But then once I enter this interval, I'm going to stall, no matter how big or small my step size is. Okay, so remember this. We're going to get back to this example. Okay, so what is important? But now look at this. We analyzed the stochastic gradient descent with respect to the empirical loss. But actually, I can plug into my expressions the out of sample, the expected loss, and I'm still going to get the same results. You can say that by just taking individual samples from my training set, I'm actually doing an unbiased estimate of the gradient of the out of sample loss, of the expected loss. So I'm going to converge to not only to the value of the empirical loss, but to the value of the actual expected loss that I would like to compute, still with the same sublinear convergence. And this is, of course, completely not viable to do any kind of out of sample loss minimization using the conventional batch mode, right? I don't have access to the entire population of points in the world. So there is some. Actually, we've seen two inherent advantages of stochastic optimization. One of them is that we don't have any dependency on n in the iteration cost. Another one, that we can actually converge to the expected loss and not to the empirical loss. Okay, the minimizer of the empirical loss. Now, what we had are basically two extremities. So if you plot here the size of our batch, so on one extreme point is the size of batch n. We are evaluating the entire gradient on the entire training set, and here in the stochastic gradient, we are just drawing one sample from my training set. Okay, and somewhere in between would fall what is called mini batch stochastic gradient, or in the language of statistics, this is called sample average approximation. We are going to draw a number of samples independently from the training set. I will call it SK. At every iteration, it will be a different set. And we are going to average our gradients on this mini batch. This as well is an unbiased estimate of the gradient. But what did we gain from this? Well, time is now, if let's say our mini batch is of size k, it's k times bigger per iteration. So if I think of this term as an estimator of my gradient, by averaging more numbers, what do I reduce? So it's an unbiased estimator, right? Bias equals 0, but the variance of this estimator will be reduced by the size of the mini batch, by the law of large numbers. So actually, I'm reducing what is called the gradient noise. Of course, I'm paying by consuming more time per iteration. So we'll see this trade-off once we have a slightly more delicate analysis of the convergence constants. Okay, so this is how the mini batch stochastic gradient will look like. I'm splitting my iteration into two parts. So let's look at the internal iteration. This is called actually iteration. I'm simply running over my entire training set in strides of k, capital K. Okay, so let's assume for simplicity that n is divisible by k. Okay, just for simplicity. So k is the size of my mini batch. I'm assuming that it is fixed. We'll talk about alternatives in the sequel. So I'm just running the first k samples are going to be the gradient estimate in iteration 1. The next k samples in iteration 2. The next k samples in iteration 3, and so on until I crunch all my training set. Okay, and then I repeat the process. So I have been exposed to the entire content of the training set. So I will start over, and this basically outer iteration is called an epoch. Okay, so I have epochs and internal iterations running over the epoch. So basically, within one epoch, I have seen all the training set. Within a single iteration, I have seen a portion and a disjoint portion of the training set. Now, of course, I don't want to create any biases. So from one epoch to another, I will randomly permute my training data. So basically, it means that at every epoch, this estimate will take completely different samples from the training set. Okay, of course, there are many different ways to actually program this, but this is also one of the ways to randomly permute the data and then run in sequential batches, which is more efficient in terms of memory. Okay, so this is our mini batch stochastic gradient, and more or less we could stop here. There are many interesting heuristics that you have seen that can accelerate it by using momentum, by adapting the step size, what is called the learning rate in machine learning literature, per parameter, like other grad does, for example. But let's see what else slightly more theoretically justified we could do. For example, we can try doing second order optimization, like we have seen before. And in this family of second order optimization, we had inexact Newton, right? We compute the Hessian, and then we invert it approximately by solving approximately again this optimization problem using, for example, a few iterations of conjugate gradient descent. So it's a quadratic problem. We don't actually need the Hessian. We always compute the Hessian product with a vector. This is done using a process that resembles backpropagation. And we can adapt it to the stochastic setting. So if we adapt this to the stochastic setting, what we had here is the gradient let's call this GK, and we have the Hessian, let's call it HK, okay, times D, of course. This is the product of the Hessian with the vector D. And we need a few iterations of these. So we can do a mini-batch approximation of the gradient, a mini-batch approximation of the Hessian product, and of course, in order for the curvature to be accurate, we'll need a certain amount of samples in my batch. But definitely, this cannot be one sample. It has to be tens or hundreds of samples. So the complexity here. So let's assume that this T nabla is the amount of time it takes me to evaluate a single gradient. Okay, so the complexity of evaluating GK is the size of the mini batch times this unit of time that it takes me to evaluate a single gradient. Now, for the Hessian, let's assume that there is some constant gamma that costs me to evaluate a single Hessian or a single Hessian product in terms of the gradient. So usually Hessian product takes more than the gradient, and this gamma is exactly by how much more. Okay, so it's a multiplicative factor. Now the iteration cost will cost me the number of Hessian products times the number of internal iterations, let's say from 5 to 50, something like that, plus the cost of the gradient. So I evaluate the gradient once, and then I do, let's say, 50 iterations to solve approximately the Newton system. And in every iteration, I need the Hessian product. Okay? So this is the complexity I'm going to pay here. Now, in order to reduce this part is costly, right? Well, so just before, let's express it in terms of this quantity, which to me is just a unit of time. It will be number of inner iterations times this constant gamma plus 1 times the size of the mini batch times the cost of the gradient. Now what I can do, I can subsample this sample and evaluate the Hessian product on a smaller set, which is conditionally independent of the bigger set, in order to not to bias my estimates. And then I will have this factor S prime k, which is the subsampled mini batch, over the size of sk popping up here. So of course this iteration is still costlier than the regular mini batch stochastic gradient, but I might need a smaller number of iterations to converge. Yes.
This subsampling is not equivalent to just reducing sk?
No, the gradient is still so. Subsampling is not equivalent to just reducing sk, because the gradient is evaluated on the full sample and the Hessian is evaluated on a subsample. Again, because the Hessian is the costliest part, and it is multiplied by the number of internal iterations. Of course, this assumes that this size is quite big to start with, in order for this reduced size to still give me an accurate estimate of the curvature. The question was essentially, if I can summarize it correctly, correct me if I'm wrong, what is the advantage of using second order information? So we know, and compared to the increased cost, of course, what is the right trade-off? So let me answer this question once I mention another second order or approximate second order technique, which was the Gauss-Newton approximation, and then I'll try to give an answer together to this to this question. So basically, remember, just in batch mode, going second order increased our convergence rate from linear to quadratic. Okay, so if we could get quadratic convergence here, that would be magnificent. Unfortunately, we cannot. But so second order methods are not as appealing here as they are in batch mode. So another second order, or let's say second order based method, was what we call Gauss-Newton approximation. I just remind you that we wrote our loss, we decomposed it as the composition of the loss function itself, which is typically convex and nicely behaving, and the model, depending on the parameters theta, which is an ugly neural network with lots of nonlinearities. It's obviously highly non-convex. And then we approximated the Hessian by taking the curvature only from the red part of the function and using first order approximation, a linearized approximation of the blue part. So we can take this Gauss-Newton matrix and just estimate it on the subsampled mini-batch, as we did with the Hessian itself. So this would be the Gauss-Newton subsampled stochastic Gauss-Newton matrix. And of course, we don't need the matrix itself. We need only its products because we are going to solve the Newton system using an iterative method. So we actually need to compute the product of H tilde K with some direction D. So we never form and store this matrix explicitly, of course. Otherwise, it could be too costly. And then there is another technique that we have seen, which is quasi-Newton. In quasi-Newton, we had essentially we replaced the Newton iteration with scaling the gradient by an approximation of the inverse Hessian, which we constructed as a successive approximation. We used first-order information to update our estimate of the inverse Hessian. So this was our scaling. We actually built a technique, or it's not. It was slightly before, as it was the BFGS technique that was introduced in the 70s, that guarantees positive, definite, and symmetric update of the Hessian model, of the inverse Hessian model. Okay, so what we had in the LBFGS variant, in the limited memory variant, that we actually never explicitly construct and store this matrix. We multiply this matrix with a vector using a recursive scheme that doesn't cost us n squared, basically the number of parameters squared to compute and to store. What it gave us, at least in the batch mode, was superlinear convergence. So we converged with the constant c to the power k and c going to 0 as the iterations progress. So it was faster than linear. If we take a stochastic approximation of the quasi-Newton technique, we can again do a mini batch approximation of the gradient. We can still use gradient information to do updates to the inverse Hessian model. The only theoretical result that exists, at least as of today, is a sublinear convergence result. So essentially, in terms of the convergence rate, we didn't gain anything, right? So it's the same order of magnitude. It decays in the same form. It's a sublinear convergence like stochastic gradient, and of course the iteration is costlier. But the iteration using second order information, this is true for quasi-Newton, for Gauss-Newton approximation, for inexact Newton, we have a better constant. Okay, so we remember that we started with Newton and second order techniques to tackle ill-conditioned problems, because gradient descent is not scale invariant. It is not invariant to reparameterization of the coordinate system. So we might get very badly conditioned Hessian, very badly conditioned problem, which will take many iterations of gradient descent to basically until we converge to anything reasonable. And Newton was this optimal linear reparameterization of the problem. So in the case of stochastic approximation, we don't have such strong theory that we had in the batch mode, but still we can actually empirically observe that the convergence constants are much better using second order information. So if you can afford it, you should use it. Yes, a question? So specifically talking about accelerated gradients, or what is called Nesterov's momentum acceleration, this is a purely first order technique because it doesn't use any second order derivatives. In Nesterov's iteration, there is no second order derivative, nor any approximation of second order derivative appears. It's just a smart way of taking advantage of first order information. So again, I hope this at least gave some, of course, very unsatisfactory, but the best answer I could give you is that second order information helps, not by dramatically changing the rate of convergence, but changing the constants. So which which is quite important. And actually, if we are talking about some optimal preconditioning, so we talked about linear preconditioning, and this is something that Newton descent did, and there is nothing better than you can do with linear transformation of the coordinate system than Newton. Things change a lot when we talk about nonlinear preconditioning. And one of the ways, which is very typical for estimation problems, is to consider some kind of Riemannian geometry that is associated with the problem, which in estimation problem relates to the Fisher information matrix that serves as the Riemannian metric. Again, this might sound Chinese, I'm just giving a teaser. And then we can do optimization. So Newton essentially changed the metric of our space. It scaled the metric globally. We can actually change the metric locally. And then instead of a scaled Euclidean space, we have a Riemannian manifold with a metric that depends on our location in the space. And we can actually devise a gradient descent algorithm that will depend on this varying metric in space. This is called natural gradient. It is a very interesting method in batch mode, and it is probably even more interesting in the stochastic approximation mode. Again, it is an area of active research. If you are interested, you can take a few papers on this regard. Actually, there are so many unknowns about what is the right way of using second-order information, or actually how to work with classical optimization techniques for these big data problems. It's an area of active research, and there are very interesting results coming from recent years' research. Okay, so let me address one problem that we haven't discussed yet. How do we select the step size? Okay, so currently we always wrote somewhere in the definition of our iterations, select the step size eta k. So let's say at least a few words. How do we select eta k? So a naive selection would be just to select a constant. Let's say we are keeping this eta k equals to some fixed eta all the time. Okay. So in batch mode, remember I showed you some result. If we have an m strongly convex problem with m Lipschitz gradient, which essentially means that if the function is C2, it means that the Hessian, the smallest and the biggest eigenvalues are bounded by m small and m capital respectively. And if we select the step size smaller than 1 over this Lipschitz constant m, then we are guaranteed to have what we call linear convergence, right? This geometric series. And the rate is governed by 1 minus eta m, right? So remember eta, let's say we selected eta to be 1 over m, the biggest eigenvalue. Here we have m, which is the smallest eigenvalue. So we get exactly 1 minus the 1 over the condition number of the matrix, which was one of the reasons why we actually adventured into the second order length, because we had slow convergence for badly conditioned problems. Okay, so this was exactly the same result that I showed you before. But you see here we have dependence on eta and on some properties of the function. Okay, so we get linear convergence in this case. But the problem is that this bound m, of course, for a quadratic function, the Hessian is constant. So this Lipschitz constant is fixed and at every point in the space. Lipschitz constant is a global property. So if I have a gradient that has a very bad scaling in one point in the space, then I need to keep that constant everywhere, and this limits my step size. So it might be that in some places I can do much bigger steps than this naive analysis prescribes me. Okay, so I would like to do some kind of an adaptive step size, and this is done by what is called line search in batch optimization. So line search does the following. I'm going to define a one-dimensional function. So once I selected the descent direction, which is this dk, so I'm currently standing at point theta k, and I'm going to make a step of size eta to the direction dk. So I have a one-dimensional function. Let's just call it phi eta. Okay, and I can simply say, let's minimize this function. Minimizing a one-dimensional function is not such a big problem. There are many algorithms that require the function itself or maybe its derivative. There are different ways of doing it. It's called line search. Actually, we can do search in a subspace of the few previous descent directions, and this subspace search is called CSOP. Actually, if you are interested, I can refer you to papers. This is a very interesting, in my opinion, potentially very fruitful research direction to try adapting subspace search that works exceptionally well in batch mode to the stochastic setting. Okay, I think nobody really did it seriously until now. The problem is that this typically adds a few tens of function evaluations to the iteration cost. Functions or gradients depending on the specific choice of the line search algorithm. So what is done instead is what is called inexact or backtracking line search, or also known as Armijo rule. So again, let's define our function on this array eta greater or equal than 0. Okay, so we have an array starting at point theta k and going in the direction dk. So I'm going to subtract the value of the point of the function at theta k. So I'm going to get a function that goes under 0 initially with this slope. Okay, so this slope is just the directional derivative of the function L in the direction dk. Okay, which is just the inner product of the gradient with the direction dk. Okay, and then I will define that. Let me show it to you graphically. So this is my function, which I draw in orange. This is my phi eta. Okay, so it starts by going down, then it can behave wildly. So I would like to draw this linear function, which is simply a linear approximation of the function based on the slope at point 0, right? It just uses the gradient, the first order derivative at point 0. I will multiply this slope by a factor sigma smaller than 1 but bigger than 0, let's say typically 0.3. So this will give me not as steep decreasing line as the blue line. Okay, and I will say that it would be sufficient for me to get my function between these two lines. Okay, so for example, a point here will be okay, a point here will not be okay, right? Because here I'm getting a point that is between these two lines, and here I'm not. So what I can do what is called backtracking line search. I will start with some initial big value of eta, and I will check this condition, which is very easy to verify. So if this condition is violated, I'm not between these two lines, I'm going to shorten my step size by some constant factor beta, let's say 0.2. Okay, I'm checking it again, still not satisfactory. And checking it again unsatisfactory. Then I'm shrinking my step size, checking again. Okay, here I declare sufficient decrease of the value of the function, and I'm done. So typically, instead of tens of iterations, it will cost me just a few iterations inside the line search. So it is much faster. Okay, so this is something that is typically done in batch mode. Because in batch mode, the descent direction has basically, it costs us quite a lot of time to compute. So let's take the maximum advantage we can from this descent direction. Now, in mini batch mode or in the stochastic mode, it's not necessarily the case. So it is quite unusual to find excessive use of line search in stochastic optimization algorithms. But let's see what happens with constant step size. So with the constant step size, suppose we have a mini batch S, and what we have on this mini batch S is an unbiased gradient estimator, meaning that the expectation of this random vector will be actually the expectation of the loss, right? Of the gradient of the loss. So the variance of this estimator is some sigma squared. So we call it gradient noise, and this gradient noise can actually be reduced, remember, by taking a bigger mini batch. Okay, so it scales down in inverse proportion to the size of the mini batch, and I can compute, of course, the second order moment, also adding the squared mean of this estimator here. So the theoretical result for the mini batch stochastic gradient tells us this. In the expectation, my optimality gap at kth iteration will be upper bounded by two terms. So one term has this geometric behavior in k, and it depends on my choice of the initial point. Okay, so usually this will be something very bad, very big constant, and it will shrink very fast as k progresses. okay, until this second term becomes less. So initially it is dominant, but then the first term starts dominating, and the first term is no more geometric. Can you see it? It's no more geometric. Basically, it's just a constant. So once I got to this regime where the first term is dominant, I cannot improve my result anymore. So the optimality gap will stall. It will remain floating around that point. Okay, this is exactly the behavior we observed in our plot. Remember, so let me just show your plot here. So initially we had very fast convergence, like in that example with the second order functions, and then we stalled here. So this is unfortunately a linear plot, so we don't really see that the function remains constant here. It oscillates, but it doesn't progress. So basically, we have linear fast convergence here because of this geometric term in the second part of the bound, and then we just stall because of the gradient noise. Okay. Question? No. So let's. Okay. So let's again have a look at this convergence result for stochastic gradient or mini batch stochastic gradient. So let's see. Basically, we have two knobs to control the constants here. So first of all, we have pay attention that both the geometric, basically the constant appearing in the geometric term here, and the constant appearing in this first term here, they both depend on eta, on our step size. We assumed fixed step size, if you remember. So we can actually control the size of eta. So for small eta, we are going to have slower initial convergence because this constant will be bad. It will be closer to 1. But we'll stall at a more accurate result because the gradient noise will be reduced. Okay, and if we have a big eta, we'll have faster initial convergence, but then we'll stall at a less accurate result. Okay, now another knob we have is the size of the mini batch, which of course controls only the sigma squared. Remember, it will be sigma squared over the size of S, right? So it controls the standard deviation by the square root of the size of the batch. So if we have a small mini batch, we will stall at a less accurate result for the same value of eta because obviously we have a bigger gradient noise, but the iteration cost will be smaller. And for a bigger mini batch size, we'll have more accurate convergence, but we'll have a higher iteration cost. So you can do the math yourselves, and we can see there is an interesting trade-off here between basically between these two parameters that we can easily control, the step size and the mini batch size. So what this leads to is a very, I would say, naive but a very effective technique for adapting the step size. We can have decaying step size. So decaying step size, typically, if you want to be able to prove something, we demand that the sequence of step sizes eta k decays fast enough. Okay, and fast enough is expressed by saying that the sum of their squares sums to a number smaller than infinity, but not too fast. So we want this. We want the sum of eta k's to sum to infinity. Another tool that we can use is to gradually increase the mini batch size. So we can do the first steps inexpensive with a small mini batch size, and then once we start stalling and we can monitor the progress of our minimization algorithm, we can monitor the values of the loss function, and once we see that we started stalling, we can increase the mini batch size or decrease the learning rate, the step size, or do both. So basically, this is still a very active research area. So there are many interesting things that can be done, and you have seen in the tutorial that there are also some nice tricks that can be done with momentum in order to converge faster. But there is not so much theory in momentum-based techniques. Of course, there is a lot more to say about optimization, but I think, at least to my taste, this was more or less what I wanted to share with you within the scope of this course.